All right, my Griffins, video number 8. This is 8 is great. This is the biggest, baddest, most important video of the unit and the last one. We will talk about nuclear shielding and effective nuclear charge, and then we will describe the trends in atomic radius, reactivity, ionization energy, and electronegativity, both across the period and down a group. It's a lot to do. Let's get started. It's going to be a long video. Sorry about your luck. Trend number 1, atomic radius of the elements. So atoms get smaller as I move from left to right. This is a perfect graphic. As I go down, they get bigger. As I go across, they get smaller. Why that is, that's the hardest trend to do. So the truth is, because the effective nuclear charge is increasing across the period, pulling the valence shell closer to the nucleus. Milks what on earth is effective nuclear charge. We haven't even talked about it yet. So let's talk about it. Effective nuclear charge, just what it's saying. Nuclear charge, we know is protons. We know protons, positive magnets, are going to pull on negative magnets. So effective, how good are they at doing what they're supposed to do? Okay. Are they pulling well or not? So when I go across the period, the effective nuclear charge will actually go up. So what's happening now is, and we actually have to talk about shielding a little bit too. So let's get into both. Okay, shielding is, I'm going to draw 2 atoms real quick. These are just side notes for your learning, probably the most important learning of the entire unit. So let me draw lithium. Lithium has P3N4. And then he has 2 valence shells. And he's only got 1, 2, 3 valence electrons. And then as I go across, I'm going to stop over at fluorine, right? And fluorine is element 9, so he's got P9, and he's got 10 neutrons. And he, again, is only going to have 2 shells. Now, I'm not going to necessarily draw this one smaller because it's smaller. But look, I just want to show you that he's going to have his 2 and then 7. 3, 4, 5, 6, 7. So this is what's going on. Now, here I have this 3 positive magnets, and they only got to get through 1 shell to get to that outside shell. So they are going to be able to pull pretty well. There's not a lot going in between the protons and the outer shell. And then again, as I get over here, P9, let's be honest, 9 protons are going to pull much harder than 3 as far as pulling in. And then here we go, ready? Same, look at that. Only 2 electrons in between the 9 pluses and those 7 outside pluses. So that's what we call electron shielding, whether you have it or you don't. Okay. So as I go across the periodic table, my shielding does not go up. Okay. 3 protons have to blast through 2 electrons, these guys, and 3 is going to beat 2 all day. Okay, but then relative, as I keep going across, now 9 protons has to get through 2 electrons to those outer ones. 9 is going to get through 2 a whole lot better than 3 is going to. And notice those kernel electrons, those 2 kernel electrons for both, not a lot. Not a lot going on there. Okay. Now I wish this would let me just move this whole thing. It's going to make it click. So let me go back, get you to where you're supposed to be with your notes. I wish I could just move this, but going down a group, let me show you what happens when I go down a group so you can understand what shielding really is. Okay, and that looks terrible when I redrew it. It's a problem with drawing these things. So let me just redraw. I was going to draw it sideways and tell you it's going down, but that's tough. So let me make some room. Let me do P3 and 4 again. And this is, I'm going to start with lithium. So there we go. There's my We like it when it's drawn a little bit better, right? Smartboard's acting funny. And I like to actually, I should color code these things because we're still new. So P3, N4, my nucleus. And then my shells here, 1, 2 shells. We have some electrons in there. We got 1 out here and 2 here. So now when I go down the group, let me pick one, and I'm going to let's do potassium is K. Potassium is element 19. So he's going to have, switch to group, it's going to have 19 protons. And its mass is 39, so he's going to have 20 neutrons. Okay, and then I need energy levels. So potassium is a 2881. So 2, 8, 8, 1. You guys are going to have to forgive me. I know you're going to hate me, but I think it's super important that I take the time to draw this stuff out and talk about this terminology so that you're really getting out of these notes what you need. So 1, 2, 3, 4, 5, 6, 7, 8. And then the next one has 8, 4, 5, 6, 7, 8. And the last one only has 1. Okay, so we talked about effective nuclear charge. And effective nuclear charge and shielding go hand in hand. Okay, so I have nucleuses. Let's be honest, my P3 is not nearly as strong as my P19. We would think that 19 protons can pull much stronger than 3. But look, I literally got wider. This one's kind of obvious. It gets wider in atomic radius as I go down because I have more layers, right? Of course. But there's something else going on, and this is what we call shielding and how it affects my nuclear charge. So my effective nuclear charge. Now, here, my P3 has got to get through 2 valence electrons to get to that outer shell. I know I drew the electron on the bottom, but that distance to the outer shell is not very big. I only have to go through this one level. So we wouldn't say that that has a lot of electron interference or shielding relative to what's going on in potassium. So now P19 has way farther to go with those protons pulling on that end valence electron. And look at all of this interference. All of these electrons are in the way, right? So when we're talking about being able to feel this, this is like the analogy that I grew up with is like we have 19 magnets in the middle, but look at all the paper clips I already picked up, and they're all surrounding it. Am I going to be able to pick up another one just by touching down without removing the paper clips as well? There's a lot going on here with all these electrons that these protons positive have got to pull through. So 19 protons already have 18 electrons being like, yo, I feel you, what's good? And that's a ratio that's not so good as far as being able to get that 19th electron to come on board. Here I have 2 electrons and 3 protons. The distance is way smaller, and 3 can get through 2 better than 19 can get through 18. Okay, the difference there is much less. If you were to do, 2 divided by 3 and 18 divided by 19, the numbers are going to be drastically different. Okay, so shielding is how much of this interference is going on. There's multiple levels of interference in all directions, and it's full of electrons. So this is like radio interference. There's something in between the positive pole protons and that outer piece. We call that interference. So this is what we call electron shielding. These electrons are forming this barrier between the center nucleus and this outside electron. That barrier is all this space here. That barrier is making it so this nucleus doesn't do its job as well of pulling in. That's its job, is to pull in electrons, keep them there. 19 protons should be doing a better job than 3. Let's be honest, 19 is stronger. But as I go down the periodic table, my effective nuclear charge is going to go down because my electron shielding is going way, way up. I'm building this layer of impenetrable electron charge. It's almost like this layer of fat, right? You just can't get through this stuff. This pull on the positive is just can't touch that outer negative as easily as it can at the top. So the top's going to be smaller. And of course, straight up layers just make sense. But now when we back up, now that we have a feeling of what this electron shielding is, it helps re-explain what's going on when I go across, because now my effective nuclear charge is again going up because my shielding is staying the same. I have the same number of energy levels, more protons. So my effective nuclear charge is actually going up. Having more protons does make a difference when I go across the period. When I go down a group, it doesn't. So the atoms get larger as I go down the group. Why? Because my effective nuclear charge is decreasing because my electron shielding is going up. The shielding increases. It's being shielded from the nucleus, that outer electron, more, and it can just get wider. Plus, obviously, I'm adding layers and layers and layers of electrons like I would an onion. Okay. Trend number 2, electronegativity. Revisit, electronegativity is the ability to attract another electron, hence how thirsty am I. So electronegativity is going to increase from left to right. I am more thirsty as I go across because I have a stronger effective nuclear charge. Those 9 protons only have to get through those 2 inner kernel electrons. So all those other electrons can feel that nucleus really, really good. They can feel the positive vibrations. It's almost like it's the sun in the middle with no clouds, and everybody else can really feel the rays. But if I add all those layers, that would be the clouds. The sun in the middle doesn't get through the clouds as well, and you can't feel it on your face quite as much. Okay, I don't know. That one just came by me now as I was thinking about it. Okay, effective nuclear charge is increasing as I go across the period. Okay, electronegativity values decrease as I go to the bottom, because do I really want another electron when I get bigger and bigger and bigger? No. Okay, effective nuclear charge is decreasing because my shielding is going up. Okay. Okay. Trend number 2. Electronegativity values to relativity. High electronegativity values. High electronegativity value means that it's very reactive. It's highly reactive, and this is for non-metals. Okay. Low electronegativity is values that mean the reactivity will be high for metals, because we got to go back and just clarify these. Notice these are worded very similar. High electronegativity values for the reactivity will be high for non-metals. How thirsty am I for an electron? Okay, high electronegativity. Non-metals really, 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 really want another electron. Hence, high electronegativity will make it very reactive. Low electronegativity is the opposite for metals because they don't really want another electron. So they're going to be very, very low. If that's the case, the lower it is, the actual more reactive the metal gets, because the metal wants to lose electrons anyways. So if it don't want one, it actually wants to get rid of one. Okay. Here it says circle which atom in the pair has the greatest electronegativity. Use table S. I'm going to do a few of these and I'm going to let you do the rest, even though it's in the video, just for your own sake. So table S, flip it over. Lithium, Li, it has an electronegativity. So we're going to look this right up. And that is going to be a saying I use a lot. Remembering the trend in electronegativity as I go across, this isn't something you have to memorize. You can look it up. Pick 2 elements in the same period. Look up their 2 electronegativities. Lithium. Lithium's electronegativity is 1.0. And potassium K, his electronegativity is 0.8. Just looked it up. And so guess who has the greatest or highest electronegativity? Well, lithium does. It's 1.0 compared to 1.8. I'll do 2 more and then that's it. You can do the rest. Sodium Na is going to be really low wherever it is. Na is element number 11. It is 0.9 for Na. And then oxygen, non-metal, definitely going to be higher, is a whopping 3.4. So oxygen is way higher. Guys, I am just looking up their electronegativities. Okay. Do I even really need to do another one? Look them up, circle the one that has the most. That's simple. Let's move on because this video is going to be too long. I just had to get into a lot of that stuff about what effective nuclear charge is and shielding is. So let's hopefully that helped. We'll do it with people in class so you can see what's going on, and then hopefully it'll really click. Ionization energy needed to remove an electron. So in other words, how tight am I holding on? If I'm holding on real tight to my electrons like a non-metal would, it's going to take you a lot of energy to get my outer electron. If I'm a metal and I want to get rid of my valence electrons, guess what? I'm not going to have a very high ionization energy. I want to get rid of it anyways. Okay, so it increases as I go from left to right because, again, same thing. As I go across from left to right, my effective nuclear charge is going to go up. My shielding is going to stay the same. That's why my effective nuclear charge is going to go up. Reason and logic, the reasons are all the same. We just got to be able to state them. As I go down the group, the ionization energy is going to decrease from bottom to top. Well, why? Because the effective nuclear charge is decreasing. The protons in the middle are not doing a good enough job of holding on to that far electron. So is it going to take you a lot of energy to take that far electron if it's really, really wide and really, really far away? Nope, not at all. So away it goes. So again, here we're going to circle these up. I'll do 2 and you'll do the rest. Okay, you will do the rest for full credit, please. I don't want to take away credit. You just do it real quick. You're going to have to do it in the practice anyways. Sodium, first ionization energy is the first one. It says first ionization energy. Na is 496. And oxygen is 1,314. So who has the highest first ionization energy? Oxygen. He don't want to give up any electrons. Be and Ba. Be is 900. And Ba, barium. Where are you, Mr. Barium? Barium. Come on, find barium. Seem to take it too long. Where is Ba? I pity the food. Where's barium? See, Be. Oh, Ba is way down, 56. That's why. Element 56. Way down. 56. Barium 503. So Be has a greater first ionization energy. We are so close to being done. Milks, let's hurry up and get done with this video. Metal atoms have low ionization energy and electronegativity due to the Z effect. We're not really going to worry about that word ever again. They're prone to losing valence electrons on their own. So losing electrons means they'll have a negative charge particle. That is wrong. They will have a positive charge particle, Milks. Put a positive there, and I got it right here, right? Therefore, the net charge. Oh, wait, I get it. No, wait, that's not right. Losing a negative charge particle means they will be positive. I see now. It's been a long day. Non-metallic atoms form ions, ionization energy, and electronegativity due to their Z effect of being large. That's just talking about how good the protons are and the nucleus is at pulling. They're prone to gaining valence electrons. They're gaining a negative, therefore their metal will be negative. Their ion is larger. There's that picture again in color to help you figure out what happens to the ions. And oh my God, finally, done. Sorry this video was so long. Really a lot of important stuff going on. Let's make sure we learn it all and know what's up. So with that, see you.